All right, I'm gonna work on the example we did from the exam, and I'm gonna go through the problem that was on the ice for me to tell you what was the trick and why the method that I did was basically a little tricky. So if we look in this table, so what I said before, for you to determine if we have a positive or a negative control, what I do, I check the wild type and I see if there was a transcription when my regulatory substance was absent. And here, my regulatory substance is nitrite, and when it was absent, we had transcription. That tells me it was a positive control, right? Then I look at one of the mutants that I want, and I see that when the substance was absent, we had transcription, but then when the substance was present, we didn't have transcription anymore. So this gives me an insight that the presence of the substance is repressing transcription. So this was a positive repressible control. And that's why D was the right answer. Now, just to notice right here, in mutant B, you guys notice that we have no. And this is because we had a mutation at the promoter. Every time you guys are gonna see, let's say I have a gene called GOR with a big P and a negative, that means my mutation is at the promoter. And we know that when we don't have a promoter, we cannot have transcription because promoter is where my RNA polymerase is gonna come and sit, and then it's gonna transcribe my gene. But if my promoter is broken, it means I cannot do anything, right? So it's basically why every time you guys see in a mutation or a mutant sequence, you guys see a mutation next to the letter P, that means you guys have a mutation at the promoter site, and that means we cannot have transcription in any way because my RNA polymerase cannot bind, right? So this was my method for the exam. Now this is what was on the ice. We're gonna go through this applying my method, and I'm gonna tell you why it was the opposite. So looking at this, when the substance was absent, we had transcription. So that tells me I have a positive control. Then I look here, let's say, and when it was absent, I had transcription, and then I look here, oh, I still had transcription after my substance was there, so it didn't do anything to stop transcription. It kept it going, so it's inducible. And as I said before, we see here we have a mutation at the promoter, and we notice, oh, no and no. Just because when there's a mutation at the promoter, you cannot have transcription in any way, right? Not with a substance and not without it, because the promoter is the key part of the gene transcription. All right, so doing my method, we got positive inducible, but the right answer was negative repressible. So let me tell you why. So if you look at the mutations here, I noticed that in mutant A, I have a mutation at the site R. And I did put a picture in the PDF that has the remarks. That's like sequence R is the regulatory protein sequence. And what it does, it produces my regulatory protein, and it basically dictates what my regulatory protein does. So this sequence R is responsible of producing my regulatory protein for me. Not only that, it tells my regulatory protein how to do it. So it tells my regulatory protein, you're gonna act positively and inducibly on this transcription. But if we notice here, in mutant A, we had a mutation at R, at this sequence, because capital P means promoter, capital R means the regulatory sequence, capital O means operator. Those are universal letters used. So every time you guys see a big R next to a gene name, this means we're talking about the regulatory protein sequence. And in A, I had a mutation at this sequence specifically. So this was basically broken in this case. When this is broken, the regulatory protein that is produced is basically doing the opposite of whatever it was originally supposed to do if R was not broken. So whatever I was seeing here, like the way this regulatory protein is working and what I'm seeing here in this table is basically the opposite of whatever it was supposed to be doing if the R was not broken. But R was broken here. So what I'm seeing in this table is basically the opposite of what it should be doing. So when I got positive inducible, yeah, that's right, because I followed what I'm seeing in the table. But what it truly does is the opposite of this, because I had a mutation at the regulatory protein sequence, so I would just flip it. So it would be negative repressible. Since here in the exam, if you look at the mutants, we did not have any mutation at the R site. We had one at NIT6 minus, one at the promoter, one at this gene, and one at this gene. None of these genes or sequences were the regulatory protein sequence. So whatever method I used or whatever we're seeing in the table is what actually my regulatory protein does, normally what it does. But since in this condition right here, we had a mutation at the R sequence, which is the regulatory protein sequence, then what I'm seeing in the table is basically the opposite of what my regulatory protein normally does. So I use my method to do it, but whatever I get, I flip it. It's the opposite of it because that's not what it normally does, but R was broken, so it's doing the opposite of it, right? And that's why negative repressible is the right answer. So every time you guys get a table, make sure to look if we have a mutation at the R position. Basically, normally, it's going to be, let's say, NIT 2R negative. Basically, it's going to have a big capital R next to it that indicates the regulatory sequence, regulatory protein sequence. But if he didn't give you the capital R, he would, let's say mutant A produces a non-functional regulatory protein sequence called NIT6 negative. Then you would know, okay, NIT6 negative means we have a mutation at the R site. So basically and often it's gonna be big P for promoter, big R for regulatory sequence, big O for operator. But if he doesn't include those capital letters for you to know like where the mutation's taking place, he's gonna mention that, let's say, NIT6 protein means it's at the regulatory sequence, and you would know to flip the effect of whatever's going on in the table.